Hello, calculus fans. So we're going to come up with a new definition here. We're going to call a series absolutely convergent if, when we put absolute value on the terms, we get a convergent series. So let's give an example. The sum of minus 1 to the n over n squared, that's absolutely convergent because if we put absolute values on the terms, we lose the minus 1 to the n, and then we get a convergent p-series. Now this series is convergent by the alternating series test because the b sub n's is equal to 1 over the fifth root of n decreases to 0. I'd like to start using this notation to mean two things, that the sequence is decreasing and is going to 0. But it's not absolutely convergent because if we put absolute values on them, we get a divergent p-series. P is 1/5, which is less than or equal to 1. Now we have a theorem about absolutely convergent series. The theorem says that if a series is absolutely convergent, then it is convergent. All right, let's go ahead and prove this. Let's suppose that we have an absolutely convergent series. Now, we know that a sub n plus absolute value of a sub n is bigger than 0, but less than 2 times absolute value of a sub n. And this is true because absolute value of a sub n is equal to either negative a sub n or positive a sub n. Now we know that the sum of 2 times absolute value of a sub n is convergent because we're starting with an absolutely convergent series. So the comparison test tells us that the sum of a sub n plus absolute value of a sub n is convergent. Now we can create the series with the a sub n's by subtracting these two series, both of which are convergent series. When you have a difference of two convergent series, you get something that's convergent. And we can also want to make a definition to say that if you have a series which is convergent but not absolutely convergent, that's going to be called conditionally convergent. Okay, that's all for now.